In this example of two-dimensional kinematics, we will use the kinematic equations in the vertical and horizontal directions to determine if a field goal kicker scores his goal. So a football place kicker stands 30 meters from the goal posts, and the goal post is 3 meters high. When he kicks the ball, it travels at 20 meters per second at 60 degrees above the ground initially. And we want to know, will he make his goal? As always, go ahead and pause the video and set up this problem. Do so by drawing a picture that marks all the important motions in this situation. Label any variables you think might be useful, and don't forget to select a coordinate axis so that you know what are the positive directions. Go and pause the video now. Here you can see the way that I set up the problem. I also made sure I abstracted some of these variables so that I gave them variable names. That way I can see the shape of the answer and I don't get lost in the numbers. I've marked different positions. I marked the position right at the top of the arc of the ball, and I marked where I think it will reach the point of the field goal. Now I don't know what the trajectory of this ball is, so I'm just guessing, but I'm just marking the way that I know all projectiles will fly through the air. That way, as I go through the problem, I'll have a way of referencing these different positions. Now, before I get any deeper into trying to answer this question, I have to determine what does it mean to make a goal. Well, in order for us to call this a goal, well, when the ball gets to this point, so when x2 equals d, then I want that y2 is greater than the height of my field goal. If it's less than or equal to, then I don't actually make the goal. Now, this is one way of answering the problem. We could answer it another way as well. We could say and look at, well, when does the ball reach a height of h? If it reaches a height of h when the x2 is greater than d, that's a field goal. Now we do have to be careful because this is symmetric, and so we will reach a height of h in two positions, right after the ball is kicked, and then hopefully somewhere back here, and we could call that a field goal, and we would have to be careful in the solution. So I'm going to pick this first method. This is the pathway that I'm going to choose. Let me find out how high the ball is when I get to a distance d, and if that's greater than h, greater than 3 meters, then I know I've made the goal, or the kicker has made his goal. Now I was given an initial velocity, and I always know I'm going to have to break up my initial velocity into the horizontal component, which I'll call vkx, and the vertical component, which I'll call vky. And using my trig identities, I can see that vkx, this is going to be vk, 20 meters per second, times the cosine of my angle. That's an important equation. I'll want to mark that. Similarly, I can say that vky, this is going to be vk sine of theta, and I'll want to mark that as well. That way now I'm just going to use vkx and vky, and at the end I can plug in my values and figure out what those components are. I'll just carry this vkx and vky through my calculation. Looking at my picture, I see that x2, where my ball hopefully has cleared the goal, x2 I'm going to set equal to d. I can't set y equal to h because, remember, I'm trying to determine that it's greater than h. Since this is a projectile, I know that my x acceleration is going to be 0. And I notice that I didn't mark my acceleration on my picture, so I'm now going to add that in. This is a projectile. Acceleration always points down. And so I'm going to have a y component of my acceleration that is minus g, minus 9.8 meters per second squared. I'm going to go ahead and set my initial positions to 0. So x naught, this is going to be 0, and y naught, that's going to be 0. And if I need it, I know that my velocity at the top of my arc is all in the x direction, so let's call that v1. It points entirely horizontally, so that my vy1, this is going to be 0. I don't know if I'll need that, but it is a thing I know. Now I can begin to look for relationships and equations that will help me answer my problem. Really, I'm trying to find out what y2 is. That's what I want to know. Since I know the x motion, the motion in the horizontal direction, is the simplest, I'm going to start there. I have two equations. I have x equals x naught plus v naught t, and vx equals v naught x. I should remember that that's also the initial x component of the velocity. From this equation, I'm going to plug in my values. I get d equals 0 plus vkx t, which I can rearrange to say t, my time, is just d divided by vkx. That is going to be a key bit of information. Now I've got time. I know what my time frame is for this kick, so I can now take this time and put it into my y equations and use it to find where I end up in the vertical direction. When I look at my information in the vertical direction, I see that I have an initial velocity, I have an acceleration, I have an initial position, and I'm looking for a final position. There is an equation that includes all of those things and time. So I'm going to write down that equation now. Y equals y naught plus v naught yt plus 1/2 ayt squared. Of course, I always want to turn this into an equation that fits my problem, so I'm going to substitute. This is y2 equals y0 was 0, v ky, that was my initial kick velocity. For time, I will substitute in the bit I know, d over vkx. And then my acceleration is negative g, so minus 1/2 g d over vkx squared. Now, you might look at that and say, that's not very clean, it looks very messy, but really that's just a number. I know all of the things in this equation, and now that means I've solved for what my final height is. Of course, when I plug in my values, I get that my y position is about 7.9 meters, which now going back to my problem, I look at that and I say, well, that is well above 3 meters. So sure enough, this is a goal. So in this example, we saw that even when the question was nebulous and ill-defined, by carefully sketching the situation and understanding the motions involved, we could come up with something more concrete. And that allowed us to write down equations that described our specific situation. By solving those equations, we were able to answer that initial ill-defined question. This translation is doing physics, and we will continue to practice it throughout this semester.